Good morning.
Good morning, sir.
Okay, only
Good
22
morning,
has
sir.
connected. Good morning. Okay. So today we would be start the last topic of the unit number 4, that is uh, basic line codes. Okay, I would wait for 30 seconds more. So another students would be also join this session. Then we would start this topic. Okay, now we start. So today we would be learn about the basic line codes. Before that, we have learned all the techniques that would be used, basically the analog signal to the digital one for digital communication, that is pulse code modulation, delta modulation, differential pulse code modulation, adaptive pulse code modulation. We have also gone through the concept of quantization error, and we know how to calculate this quantization error and what is the importance of this during the digital communication system. Okay, so if you have to be talk about the line code, so line coding is a process of converting digital data to the digital signal. So it is just a process for conversion of the digital data into the digital signal, because data can't be directly transmitted in the transmission media. It has to be first converted into the signal. So we assume that the data is in the form of text messages, numbers, graphical images, audio, or video that is stored in the computer memory as the sequences of the bits. So line coding converts a sequence of bits to a digital signal. At the sender, digital data are encoded into the digital signal. At the receiver, digital data are recreated by the decoding the digital signal. Then we have also learned in the lots of the method that we have learned, pulse code modulation, for example. We have to be first sample the signal, analog signal, and these samples would be using the quantization theorem. We have to be assign these the voltage levels and the quantization levels are there, and then further it would be encoded using the PCM encoder, and this encoded signal would be now after that would be transmitted to the channel. So in the sender side, we have to be just encode the digital data into the digital signal. Okay, and at the receiver, we have to again recreate this digital data from the received digital signal by requantization and the decoding, the another methods we have already talked about it. So this is the diagram that you can elaborate the concept of the line coding and decoding. You can see in this particular picture that in the sender side there is a computer has been shown as a sender, and it would be generated the digital data in terms of binary number 0 1, and it would be passed through the encoder where it would be converted into the digital signals. And this link is nothing but it is just a transmission media, and here it is, you can consider the channel is there where it would be maybe some noise or some errors could be added during the transmission, and then further it would be received by the receiver as a digital signal that would be further requantized and then decoded. But after decoding, this signal would be again reconverted into the digital data that we have actually transmitted through the sender, and at the receiver it would be received by the receiver. So this is the basic process that we use for line coding and decoding method. We know that we know how to represent an analog data into the binary, that is in terms of two symbols 0 and 1. But how do we assign electrical voltages to them? that suits the communication over an electrical line. This issue means the conversion of the these symbols into the voltage, electrical voltage, is addressed in the line coding, which looks into the factors like first one, if you have to be considered, the factor is the power and bandwidth requirement for the transmission. That is very important factor. Then second one is the ability to extract the timing information from the digital signal. Then third one is the presence of the low frequency or maybe the DC component, which is unsuitable for the AC coupled circuit. So in the digital transmission, we have to be avoid this DC component. But sometimes in some methods, there is by default involved. So this would be actually unsuitable for the whatever the AC circuits we are using for the transmission. Then fourth one, the factor that we have to be look after the during the line coding is error monitoring ability of the that particular type of line codes. So these are the four main issues that we have to be addressed during the line coding procedure. So we have to be talk about the whatever the basic line codes we have to be learned today. That is shown through this particular diagram. Unipolar line code, polar line code, bipolar line code, multi-level, and even the multi-transition. But not all we have to be learned as per our syllabus. We have to be go through the unipolar method, that is non-return to zero, polar non-return to zero, return to zero, as well as a biphase like Manchester. Similarly, for the bipolar AMI, alternative mark inversion. Then for the multi-level, we have to only learn this as per our syllabus mentioned, and for the multi-transmission MLTC. Okay. So if you have to come to the first one, unipolar NRZ signaling. In the unipolar scheme, all signal levels are on the one side of the time axis, means either above or below. Only one polarity of the signal would be possible. So in this line code, symbol 1 is represented by transmitting a pulse of amplitude A. In some books also they have mentioned the terms B. You can use either of these terms to represent the amplitude of the signal, maybe plus B or maybe A. And for the duration of the symbol, so in this case, symbol 1 is represented as the pulse of amplitude A for the duration of the symbol, and the symbol 0 is represented by the switching of the pulse. That's why unipolar NRZ line code is also referred as on-off signaling. It is also known as the on-off signaling, because only when the binary 1 is transmitted or symbol 1 is transmitted, then and then only we would be represented with the pulse, and rest of the time it would be absence of the pulse. So if you have to talk about the disadvantages of this unipolar NRZ signaling, that is, in this method there is a wastage of the power due to the transmission of the DC level, and the fact that the power spectrum of the transmitted signal does not approach zero at the zero frequency, means DC levels are present, means at the zero frequency still there is some amount of power is present. That's why it is a, you can say that wastage of power in this particular method, that we can understood with the help of this diagram. So there is the two diagrams are shown here. If you have to be talk about the left one side is, I have to show you that how the representation of the unipolar NRZ signaling you can see here, and the bit period is the TB is mentioned here. So for the binary 0 it is absence of pulse, for the binary 1 it is the presence of the pulse for the full duration, and similarly again binary 1 it will be continue the same level, when again 0 it would be come back to the 0 level, this like this. And you have to see that all the pulses of the train of pulses has been be represented on the one side of the axis, means it is represented as the positive axis. So this is the main concern of the unipolarity of the signal. So unipolar NRZ. NRZ means what? Non-return to zero. So you can say we have to be consider this bit period or bit duration. On this duration, this signal would be maintain its level. If it is binary 0, it should be maintain the 0. If it is binary 1, it should be maintain the amplitude of the A only. It should not be returned back to the 0 during this bit duration. then such kind of the representation is called the non-return to zero. Okay, and you can see that there is a graph I have shown here, a normalized power spectral density versus a normalized frequency. Okay, so you can see if you have to be calculate the normalized power, it will become the a square upon 2. So that's why it is weight is 0.5 a square, you can say. That is so that, and even you can see at the zero frequency there is the amplitude of the a square upon 2. That's why it is the DC components are present. So this is the one of the major drawback of the unipolar NRZ signal. Okay, so everyone please take the screenshot of this representation. Okay, because in the examination they would be asked by giving some binary pattern, they would be give you the task that draw the unipolar NRZ, bipolar RZ, like this 4 and 5 signaling method, line coding methods, and you have to be draw the diagram. Okay, so now we have to move to the second one, that is unipolar RZ signal. Now we have to be understood what is the difference between the NRZ and RZ. It is written to zero. So in this line code, symbol 1 is represented by the rectangular pulse of amplitude A, and half symbol width, it would be only represent for the half symbol width. That means the half of the bit duration, and other half of the bit duration would be 0. And symbol 0 is represented by the transmitting no pulse. In the case of symbol 0, it would be remains as same as in the case of previous unipolar NRZ, means it would be remains on the 0 level. So an attractive feature of this particular unipolar RZ line code is what? The presence of delta functions at f is equal to 0, that is plus minus 1 upon TB in the power spectrum of the transmitter signal. And the delta functions can be used for bit timing recovery at the receiver. Bit timing recovery of the at the receiver. This is the one of the attractive feature of this your unipolar RZ signal. However, it is also having a disadvantage that it requires 3 dB more power than the polar RZ signaling for the same probability of symbol error, because it is also having the signals present in the zero frequency. This is also having a one of the drawback actually. Like unipolar NRZ, it is also the unipolar RZ having the signals present at the zero frequency, so it will be again the wastage of some power, but it is less amount of power as compared to NRZ signal. So you can see the pattern line code for the electrical representation of this particular binary data. So binary 0 as it is shown as a 0 level, but you can see what is the difference between this with respect to the NRZ signaling is that for the binary 1, for whole bit duration, this the bit duration is what? This is your bit duration TB. But for half of the bit duration, only the pulse would be there for amplitude of the A, and rest of the half it would be again at the 0th level. Similarly, for the next one, again it is, and for the 0 it would be remains as the same at the 0 level. Okay, and if you have to talk about the normalized power spectral density versus normalized frequency graph, so you can see that your power would be reduced by 1/4. Okay, because it is not present for the half of the time, and also it has having the DC component present. Okay, in the first one it was the sync function, that's why it is you can say the 0 at the 1. This is the act like a sync function, but in the case of RZ it is not, normalized power will not represented as sync function, that's why it is not 0 here. Okay, now come to the polar NRZ signaling. Third one is the polar NRZ signaling. So if you have to talk, it is little bit different from the unipolar. Unipolar is only the signal would be either above or below the reference axis, but here the voltage are on the both side of the time axis because it is called a polar. So in this line code, symbol 1 and 0 are represented by transmitting pulses of amplitude plus A and minus A. So you can choose any one, means for symbol 1 is here chosen as a plus A and 0 as a minus A. But in some authors also have used the reverse method as well. 1 is minus A and 0 is plus A. It is only the matter of representation. But it is the main important fact is that voltage are on both sides of the timeline. So the polar NRZ non-return to zero line code is relatively easy to generate, but its disadvantage is that power spectrum of the signal is large near the zero frequency. Again, this is having the same nearly same disadvantage, that is power spectrum of the signal is large near the zero frequency. Okay, so we have to be see, and it is also seen in this particular normalized power spectral density versus normalized frequency graph. In the case of unipolar NRZ, the power level is limited to the 0.5 only. In the case of unipolar RZ, it is 0.25 only. But in the case of polar NRZ, it is increased the power spectral density near the zero frequency. That is, it is goes to as to the A square. Okay, the A square is here 1. So now you can see the representation timing diagram of this polar RZ return to zero. So and not return to zero, NRZ, polar NRZ signaling. So you can see binary 0 is represented as the -A and binary 1 is +A. And this is continue for the whole bit duration. So it is called as a non-return to zero. See, this is very important thing is that you have to be understand what is the difference between the return to zero signal and non-return to zero signal. That's why the bit duration having a very high importance. Okay, so you have to be take care of this when you have to be go to draw this kind of the diagrams. So bit duration is that for the same binary representation, the whole the whatever the binary is, for example, the binary 1 or 0, whatever it is, it would be represented on the same level for the complete bit duration, means it is NRZ signal. But for the same binary level, if it is decrease or it is bring to the 0, for half of the bit duration it is maintain its level, and then half of the bit duration would be come to the reference 0 level, means it is returned to 0. Okay, so we have to be see the another kind of the polar signaling, that is polar return to 0 signal. So this polar return to 0 scheme uses 3 voltage values: positive, 0 and negative. So each symbol has a transition in the middle, either from high to 0 or from low to 0. So in this case, we have to be 3 voltage values. Okay, positive, negative and 0, because it is return to 0 signal is there. That's why it is one more level is added. And each symbol has transition in the middle because it is return to 0. So this scheme has more signal transitions, means two transitions per symbol. Okay, so therefore requires wider bandwidth. It would be required wider bandwidth, and no DC components or baseline bending is there. And it is also having a property that self synchronization transition indicates symbol values. More complex as it uses the 3 voltage levels, so the complexity would be increased. This is one of the disadvantage of this, but advantage is that no DC component. And one more disadvantage you can consider, it has no error detecting capability. So you can see the representation of the polar RZ. If you have to talk about the polar RZ is here, the representation is very much clear. For the 0, binary 0, it would be having the -A, you can say, level, but only for the half of the bit duration, not complete, because it is returned to 0 signaling. And then rest of the half it would be come to the 0 level. Okay, and for next bit, that is binary 1 is there, it is +A for half of the bit duration only again. Okay, so it is only for half of the bit duration, TB upon 2, and rest of the half of the duration will be again returned to the 0. So in this way we have to be represent the polar RZ signaling. Okay, and so one of the, you can see the normalized power versus normalized frequency graph. It is having no power spectral power component or the near the zero frequency. Okay, so this is having absence of the DC component, but its bandwidth is large because we represent two levels per symbol, so it would be increase its bandwidth. Okay, now come to the next one, signaling, bipolar RZ signaling. Now we have to be shift from unipolar, then polar, and now it is a bipolar RZ. Okay, so bipolar return to zero signaling is what? In this line code method, it uses the three amplitude levels. Again, it is also using the three because it is a bipolar and as well as a RZ. Specifically, positive and negative pulses of equal amplitude, means plus A and minus A, are used alternatively for symbol 1, with its pulses having a half symbol width, and no pulses is always used for the symbol 0. So it is little bit different from the polar RZ. We have to be see from the diagram as well, but we have to be first talk about the property of the bipolar RZ signaling is that the power spectrum of the transmitted signal has no DC component. Again, it is having the advantage, and having relatively insignificant low frequency components for the case when the symbol 1 and 0 with equal probability. This is you can consider as a disadvantage also. And this bipolar RZ line code is also called as alternate mark inversion signaling, AMI signaling. Okay, so this is also the another popular name of this bipolar RZ, or biphase signaling also we have to be say it. So alternate mark inversion signaling. So see what is the pattern of the bit to be represented in this AMI or bipolar RZ signaling. As usual, binary 0 is represented as the absence of the signal, but when you have to be says the binary 1, so for half of the bit, means it is TB upon 2, it would be remains plus A, and rest of the half it would be again back to the 0 because it is return to 0 signaling is there. But if the next time the 1 would be came, again the binary 1 would become, this signal would be goes to the having the amplitude minus A for half of the bit period, and rest of the half of the bit period again back to the 0. So see the pattern of this bipolar RZ is very much different from the bipolar polar RZ. Okay, so here for 0 it would be 0, but for binary 1 for half of the period it would be positive amplitude, and when the next time the A1 would become, it would be goes to the negative, means odd number of ones is there at that position, it will be the positive amplitude, and when the even numbers of positions where the 1 would became, it is having the negative amplitude. Okay, you can see in the first time it is positive, then second time negative, then the third time again it is positive, and here last one it is the fourth one is a negative. But in between, if there is a 0 is came, then it would be remains on the 0 level, and there is no condition that the 1 should be come into a successive manner. You have to only count the positions of the 1, means it is a binary position, or sorry, it is a even position or odd position. Okay, and there is also the normalized power spectral density versus normalized frequency graph has shown, where you can see that there is no DC component because there is no power spectral component is present at the 0th frequency. Okay, and it is also a very large power spectral density, means A square is here represented as a 4, so it is a very large value. Okay, so and this is also one kind of the sync function is there. Now come to the another line coding method, that is a split phase, or it is also called as the Manchester coding. In this method of signaling, symbol 1 is represented by the positive pulse of amplitude A, followed by the negative pulse of amplitude minus A, for both pulses being half symbol wide. And for 0, polarity of these two pulses are reversed. And the unique property of the Manchester code is that It suppresses the DC component and has relatively insignificant low frequency component regardless of the signal statistics. So this property is very essential in some applications. So we have to see now the graph of this timing diagram of this split phase, then the concept will be more clear. So here symbol 1 is represented by the positive pulse of amplitude A followed by the negative pulse of amplitude minus A, and both would be at the half of the pulse width. We have to see that how. Binary 0 is what? Polarity of these two would be reversed. You can see here. This is very important diagram. We have to be take care of this. This is your TB upon 2. Up to this point, you have to be achieve the TB. Okay. Okay. So this see here. For binary 1, first of all, we have to be discussed as per our binary 1. For half of the bit period, it would be plus A. You can see half of the bit period is plus A. Then rest of the half of the bit period, it is a minus A. Okay. So this is your complete bit period. Take care of this. Okay. This is your complete bit period. Now, next time again 1 is coming, the same pattern would be used. But when the 0 is coming, so the polarity would be reversed. Pattern is same, but polarity is reversed. So in the case of 0, when the 0 would be came, you can see first half of the bit period is minus A, and next half of the bit period is a plus A. So just inversion of the pattern as we have represented in the case of binary 1. Okay. So this is the way that we have to be represent the signals in the case of split phase Manchester. Okay. So you can see the there is no DC component. Again, it is a very good property of this, and A square is 1. So normalized power spectral density is also uniform, and bandwidth is large, because we have to be use more levels in the one symbol, 2 levels in the one symbol. Okay. So I hope all of you drawn also this diagram, or maybe taken the screenshot. So this is the we can say the last method for the binary signaling. Now we have to go for the multi-level signaling. Okay. So multi-level line codes are also possible. So in this case, till that we have only learned the 2 level signals, means binary levels 1 and 0. Now we have to see what is about the multi-level line codes. So in this scheme, we increase the number of data bits per symbol, thereby increasing the bit rate. Number of data bits per symbol, we have to increase the data bits per symbol, as well as increasing the bit rate. Since we are dealing with binary data, we have only 2 types of the data elements, 1 and 0, but now we have to we can combine 2 data elements into a pattern of m elements, and that is represented as 2 raised to the power m symbol. So we have to just combine the 2 data elements into the pattern of m elements, that is having the 2 raised to the power m symbols are there. So we have the L signal levels, and we can use n signal elements to the create L to raised to the power n signal elements. So we have to see that one of the example, that if we have to be 2 raised to the power m symbols and n raised to the power L raised to the power n signals. So if 2 raised to the power m symbols is greater than the L raised to the power n signals, we cannot represent the data elements. We do not have enough signals. But if it is equal, then we have exact mapping of one symbol to one signal. And if the third condition you have to see, if the number of symbols are less than the signal levels, then we have more signals than the symbols. We can choose the signals that are more distinct to represent the symbols, and therefore have better noise immunity and error detections as some signals are not valid. So these are the three conditions basically for the multi-level signal. Means we are dealing with the symbols and the signal labels. So here, whatever the technique we are going to use today, that is learn MBNL. This is very important formula. Okay. So MBNL scheme is what? It is having a pattern of M data elements. M is the number of data elements, is encoded as a pattern of N signal elements. M is the data element and N is the signal elements, in which 2 raised to the power M is less than L raised to the power N. Means number of symbols would be less than or equal to, means second and third condition. Then and then only it is possible to represent the MBNL signal levels. Okay. So now we have to see one of the representation of this multi-level code. So we use the notation MBNL, and we have already defined that M is the length of the bit binary pattern, B represent the binary data, N represent the length of signal pattern, and L are the number of levels. So remember that what is the meaning of each and every alphabet. Okay. So if L is equal to B, means number of levels are equal to binary data, and if L is equal to B, then it is called a binary. If L is equal to T for 3, so it is called as a ternary. If L is equal to Q, means 4 levels, so it is called a quaternary. So if L is equal to 2 or B, you can say that it is a binary level. 3, then it is a ternary, and 4 is, it means the quaternary levels. So today we are, whatever we are going to discuss, that is a 2B1Q. So it is nothing but MBNL. Okay. So 2 data elements, binary data. N is what? N is your length of the signal, and L is Q, quaternary, means the number of levels would be 4. Okay. So you can see here there is a 4 levels, that is start from +3, +1, then -1, and then -3. So these are the 4. L is equal to 4 here, quaternary. Okay. And per signal is 1. Per signal there is a 2 data elements. M is equal to 2 is here. Okay. So we have to see the representation of the 2B1Q, assuming the positive original level. So you can see here, this is first of all, there is a transition table is important. So next bit is, that is 0001, because 2 bits are used in representing one labels. So it is represented as 00, 01, 10, and 11. There is a 4 representation is only possible, and it would be represented as the labels as 00 is +1, 01 is a +3, 10 is a -1, and 11 is a -3. This is for if it is only possible if the previous level is positive, but if the previous level is negative, then the representation is different. So 00 is then -1, 01 is -3, 10 is +1, and 11 is +3. So see that during the representation. So here we have assumed that positive original level is positive, means previous level is positive. We have to follow this table. Okay. So in this case, you have to see that when you have the 00, it would be represented as +1. Then when it is 01, sorry, when next one is a 11. So 11 is -3, directly it would be shift to the -3. Next one is 01. So again it would be shift to the +3 actually. So you can see okay, this is very important, that how we have to be represented. First we have to be considered that assuming the previous one is a positive. So when you have received the 00, means you have the +1. Okay. But when you have to be come to the next one, that is 11. So previous is the positive, obviously, so it is -3. But we have to be reached to this position. For the next level, we have to be assumed here that it is a negative one. Okay. So when the -1 and you have got the 0 1, at that condition, what is the next is there? -3. That's why it is maintained to the same level of the -3, because previous one is the negative. Then we have to come to the next level, that is 1 0. Even the previous is negative again, so we have to follow this table. So for 1 0 it is +1, so it would be goes to the +1. Okay, and now for the next one is a 0 1 and previous is a positive, so 0 1 it is +3. So this is the way that we have to draw this diagram. So for drawing this scheme, you have to always remember this transition table. This is very much important. Okay. Simultaneously, you can start to fill up the attendance as well. Now we have to come to the last scheme, that is MLT3 scheme, multi-transition scheme. If we have a signal with more than the 2 levels, we can design a differential encoding scheme with more than 2 transition rules. Okay. So MLT3 is one of them. So multi-line transmission means 3 levels schemes are used in MLT3, that is +B, 0 and -B, and 3 transition rules to move between the levels. If next bit is 0, then no transition. If next bit is 1 and the current level is not 0, then the next level is 0. Then the third, if next bit is 1 and current level is 0, then the next level is opposite to the last non-zero level. So this is the rule for representing the MLT3. So you have to keep in mind, what is the rule? When next bit is 0, there is no transition. If next bit is 1, current level is not 0, then next level is again 0. But if the next bit is 1 and current level is 0, then next level is opposite to the last non-zero level. So that is represented here. This is the typical case, and worst case has been represented here. For this, you have to follow this algorithm. Okay, so today time is not sufficient to elaborate this concept. So for the next tomorrow's lecture, I would continue this, and then we have to start the unit number 5. Okay, and today we have the test of the data communication at 3 p.m. So test would start 3 p.m. sharp on the Google form, and all questions are compulsory. We have the 30 questions, 30 marks, and that is based on the all 3 units, and every unit having the 10 questions and 10 marks are there. Some numericals are also I have included in the today's questions. So practice it with the formulas that we have learned in unit number 2 and 3 as well as the first unit. Okay, and all the best for the examination. Try to keep your internet connection proper during the examination, so you have to submit on the time. Thank you all of you for attending the lecture today.